Picture your game running 10,000 entities, all of them moving every frame. When the frame rate falls apart at that scale, the culprit usually isn't the math you're doing per entity, it's memory. The CPU can do the arithmetic almost for free. What it can't do for free is wait for the data to show up from RAM. So the first real problem I had to solve building this engine wasn't how to update an entity, it was where to put an entity's data so the processor can actually reach it fast. Let me walk through what I mean. The obvious approach, the one most of us reach for first, is to make each entity an object. It has a position, a velocity, a health value, whatever it needs. You allocate it, you keep a pointer to it, and you store all your entities in a list. Clean, readable, and on paper, fine. The trouble shows up when you iterate. Say you want to move every entity. Read its velocity, add it to its position. Simple loop. But each of those objects lives wherever the allocator happened to put it, scattered across the heap. So on every step of the loop, the CPU jumps to a new, unrelated address. And modern CPUs are built around a bet that the next thing you need is sitting right next to the last thing you touched. When you chase pointers around the heap, you lose that bet on every single iteration. The processor stalls, waiting on the cache, over and over. So the goal becomes clear. Store entities that get processed together, physically together, in memory. And that's the idea the whole system is built on. The first move is to stop thinking about individual entities and start grouping them by shape. By shape, I mean the exact set of components an entity has. Every entity that has a position and a velocity, and nothing else, belongs to one group. Every entity that has position, velocity, and health belongs to a different group. That group, a set of entities that all share the same exact component layout, is called an archetype. Once you've grouped by archetype, every entity in that group has an identical memory footprint, and that's what lets you pack them tightly. Here's how the packing works. For each archetype, I allocate a flat buffer, a fixed slab of memory. I call it a chunk, and each chunk is 16 kilobytes. Inside that chunk, I don't store entities one after another as whole objects. Instead, I store the components as separate arrays. All the positions in a row, then all the velocities in a row, then all the health values in a row. So if you're running that move loop, the velocities you need are packed end to end, and the positions you're writing are packed end to end. The CPU's bet pays off. You stream straight through memory the way the hardware wants you to. But a chunk can't just be raw component data. It needs to know a few things about itself. So the very front of every chunk is a header, a small block of metadata describing that chunk and only that chunk. What's in the header? A few things. First, how many entities are actually living in this chunk right now? The current count, because the arrays have capacity for more than they hold. Second, the offset of each component array, where the positions start, where the velocities start, so the code can find any array without recomputing the layout every time. And third, the enable and disable state of each component in the chunk, so a component can be switched off for the entities here without tearing the whole structure down. Put it together, and a chunk is a self-describing, cache-friendly unit. 16 kilobytes, one archetype, component arrays laid end to end, and a header at the front that tells you exactly how to read it. That's the foundation everything else in this engine sits on. In the next part, I'll get into what happens when an entity's shape changes, when you add or remove a component, because that's where this design gets genuinely interesting.